I will begin with a word of prayer. So, as I get up here. Heavenly Father, we thank you again for your many blessings to us, and just thank you for this day. Just ask that you be glorified in what we do and understand a little bit more just about linear algebra today, Lord. In your name I pray, Lord Jesus. Amen. So, thank you for your exciting surprise attack mission 8. Let us get into, so like what we're doing today, for the most part, is we're looking at, one of the major applications of the math we've been doing. All right, so we have this Jordan form that we can calculate for the matrix, and first of all, we have eigenvectors. All right, so the basic problem I want to talk about how to solve is a system of ordinary differential equations. System of ordinary differential equations. So let me just show you. Example 1, we could have x prime equals to say x plus y, and y prime equals to, let's say x minus y. All right. How would we solve this system of differential equations? So I will show you the way. First of all, we can trade it for a, oh, come on. Oh, these are trash. Hold on a second. Ha! There, fixed. So basically the method is to write down the problem as a matrix problem, like this. So here's my coefficient. And so what we're trying to do is we're trying to solve dr dt equals to AR, right? Where R in this case is like a vector of unknown functions we're looking for, right? And A is constant. Now I'll derive this in a little bit more systematic way once we get past this example, but basically the theorem we're going to prove in just a bit is that if AV, let's say AU is equal to lambda U, then R of t equals to E lambda t times U gives a solution to star. Now, this is what I'm calling star, all right? And this kind of solution I will refer to as an eigensolution. All right, an eigensolution. Okay, so let's use that theorem. All right, I will justify it second. I'm putting the cart before the horse here, if you guys don't mind, just to do an example right off the bat. All right, so we need to find the eigenvalues and eigenvector for A. I don't know how this is going to go. I just made up the matrix, so I hope it's got integer eigenvalues. Otherwise, I'm in a world of hurt. But 1 minus lambda, we'll find out soon. 1, 1. I reserve the right to change this matrix to make the problem easier. That is a privilege that only I have. Okay, so that gives us lambda plus 1 times lambda minus 1, which is lambda squared minus 2. Okay, it's not glorious. Okay, all right, so we have, there are two paths we could go down here. The one path, if we stay on this path, we have square roots of 2. That seems unpleasant. How can we make this square root of 2 go away? I want to make this like 4. How can I make this a 4?
Make it lambda plus 2, lambda minus 2.
Plus 2. Well, how about, I want to make this 1 into a what? Like a 3, right? And I can get that to be 3 if I just put a 3 up here, right? Which means that there had to be a 3y back over here. All right, now the problem's nice. I say the problem's nice because now we have eigenvalues which are integer, right? So I have lambda 1 equals to minus 2, lambda 2 equals to 2. We need to find the eigenvectors, all right? So let's do that. Lambda 1 equals to minus 2. So I'm looking at a plus 2i times u1, which in this case would be 3, 3, 1, 1 times uv, right? All right, so you guys tell me u1 equals to what? What should I make my eigenvector here? 1, negative 1. Very good. Now, you could go through the motions of solving the equation, or you could just write it down because it's clear. That vector, when we multiply it by that 2 by 2 matrix, gives us 0. What was the algorithm that he used? Maybe it was just raw guessing, so I can't say what the algorithm was, but my algorithm in this kind of situation is just to take the vector which is given, like the row vector, and just put a minus on one of the entries and flip them. So maybe we'll see that more in the next one. Let's see here, lambda 2, maybe not, I don't know. Lambda 2 is 2, so I'm looking at a minus 2i times u2. This is the kind of vector I'm trying to find, which is minus 1, 3, 1, minus 3. Ah, there we go. This will serve to illustrate my comment. So this time, my method of guessing for these little 2 by 2 problems, I can just look at it and write down the eigenvector. So what I do is I just flip-flop these components, all right? Instead of 1, 3, I do 3, 1, right? But it's not just that. I mean, naively, I would have minus 3, 1. That doesn't work, of course. So what I want to do is change the sign on one of my flip-flop components. And I kind of like to keep it positive, so I just do this, all right? Now the question is, does it work? Check your answer. Multiply that vector times this matrix. I get minus 3 plus 3, 3 minus 3. When I multiply that vector times this matrix, it works. It does give us 0. So there's an eigenvector with eigenvalue 2, and there's an eigenvector with eigenvalue minus 2. Now I need to tell you a little bit more about the theory of differential equations. But rather than writing it formally, I'll just tell you the theory of differential equations then says the general solution has form r of t is equal to c1 e to the 2t times my, e to the minus 2t times 1 minus 1 plus c2 e to the 2t times 3, 1. And that right there, guys, is the general solution to this problem. Now, of course, maybe we don't like that. All right, so, I like that, but that would mean that this system has the solution x equals to c1 e to the minus 2t plus 3c2 e to the 2t for x, and my y, I'm just reading this out, all right? So the second component gives me minus c1 e to the minus 2t. Oh, this marker smells like death. Plus c2 e to the 2t. And there you go. This up here at the top of the board would be the general scalar solution. Down here general vector solution. I prefer vector solutions in here just because it's easier to read, but I mean, those are the functions that I put at the top of the board in red that you could plug into that system of differential equations and you'd have solved it. All right? All right, so I want to justify this method. So I need to spend, about, I don't know, 20 minutes or so talking to you guys about calculus and matrices, right? So we should do that. So let me take a step back and talk about calculus and matrices. So basically the thing we want to kind of up our game in here a bit, I suppose, and we've talked about matrices full of numbers, right? On occasion we've looked at a matrix that had like symbols in it, but now I want to talk about, say, a matrix of functions. So we'll just think about functions of one variable. So you could think about it as like a matrix full of functions of time, something like that. So let me just give you an example. We could have something like A is equal to, I'll keep it simple, t squared, t cubed, t to the fourth, right? Here's a 2 by 2 matrix of functions, right? So what would dA dt mean? How does that work? Well, the way that works is simply differentiate component-wise. So we differentiate each component separately. So like the derivative of t is what? 1. Then we got our 2t over here, 3t squared over there, and then 4t cubed. So that's the derivative of a matrix. Have I talked about differentiating matrices in here before? No, okay, just checking. My mind plays tricks on me sometimes. So, good. And you could also integrate the matrix, right? What would the integral of A dt look like? What it would look like is the integral of t dt, the integral of t squared dt, the integral of t cubed dt, the integral of t to the fourth dt, right? Which would give us like 1/2 t squared plus c1, 1/3 t cubed plus c2, 1/4 t to the fourth plus c3, 1/5 t to the fifth plus c4, like that. Or you could write it like this. You could say that's 1/2 t squared, 1/3 t cubed, 1/4 t to the fourth, 1/5 t to the fifth, plus a constant matrix, right? We could just add a constant matrix if we wanted to look at it that way. All right, this is a math class. I should give you guys definitions. So let us write down the definition of derivatives of a matrix and so forth. So definition, if A is a mapping, let's say, from the reals to R m by n, then dA dt is likewise a mapping from the reals to R m by n, where dA dt ij is simply equal to ddt of aij. Okay, it's kind of dumb, but there it is. Likewise, the integral of a dt ij is simply equal to the integral of aij dt. Which, so all this definition is saying, guys, is that we differentiate or integrate a matrix valued function of time, or equivalently a matrix of functions of time, component-wise. And that's the definition. Any questions before I prove some things? So, you guys remember Calc 1, right? What are the big rules in Calc 1? I mean, you got your power rule, obviously, right? We just used that, didn't we? But you remember one of the big rules we learned in Calculus 1 is the product rule. So that's still pretty interesting here, right? So let's talk about the product rule. Suppose you have two matrices, both functions of time, and they're the right size to multiply. Okay, does that make sense? What I'm talking about? So theorem: if you have A, which is a mapping from, say, the reals to R m by n, and B, which is a mapping from the reals to R, let's see here, n by p, then A times B is going to be a mapping from the reals to R m by p, defined by AB at time t is what? This is very silly, but A of t, right, times B of t. So what I'm saying is we multiply matrices of functions simply by multiplying the matrix of their values. In a given semester of 221, I may forget to even define this, all right? So, but anyway, I've said what I've said. So then here's the actual interesting part. The derivative with respect to time of AB is equal to dA dt times B plus A times dB dt. And notice that the order matters because these are matrix multiplications, right? These are matrix multiplications. So they're not commutative. So how should we prove this? Well, we know the definition of matrix multiplication, right? So we can prove this. It's not a big deal. Like, what's the ijth component of this by definition? It's the derivative of the ijth component, right? So that's just the definition of differentiation. We do it component-wise. What's my definition of ABIJ? Well, you know that as well. It's the sum, k equals 1 to n, of A, I, K, B, K, J. Right? That's how we define matrix multiplication. All right. And then now we just do like calculus 1. So this is the sum, k equals 1 to n, of ddt of aik bkj, right? That's just by linearity of the derivative, right? The derivative of the sum is the sum of the derivatives. That's all I'm using there. That's a property of derivatives we have from Calc 1. Now I'm looking at the derivative of a product, right? Now this isn't a product of matrices. This is a product of component functions of matrices, right? So by the ordinary product rule from Calculus 1, I can rewrite this as the sum, k equals 1 to n, of dik dt times bkj plus aik derivative of bkj with respect to t. But if I just undo what I just did, that's nothing more than dA dt times b plus a times dB dt, the ijth component of that. And since this identity holds for arbitrary ij, the product rule follows. All right? So this is the product rule. Now let me get back to the problem of differential equations again, right? So our goal is to solve like dr dt equals to AR, where R is going to be a mapping from the reals to Rn, and A is given n by n constant matrix. All right, that's the problem we're trying to solve this week. Okay? So I just want to kind of take a moment to try to glean some general truths about this problem using linear algebra. So like first order of business, what does it mean to find a solution to this differential equation? I mean, I showed you in example 1 what it means. It means we're finding a function of time, right? Actually 2 functions of time if it's the 2 by 2 problem, that when we plug those in, the differential equation works, right? So like first of all, let's define what it means to be a solution. So definition, R is solution to dr dt equals to AR if, let me say R naught for the sake of making it look different, if dr naught dt is equal to AR naught. In other words, a solution to a differential equation is a function, a vector valued function, that when you plug it in, it works, right? So here, this is a vector of functions, right? In time t, let's say. I mean, t doesn't have to mean time, but I just by default think of it as time. All right? So, theorem. A linear combination of solutions is a solution to dr dt equals to AR. That's a theorem we can prove. All right, let's work that out. So proof goes like this. Assume that you've got R1, R2, Rn solutions of dr dt equals to AR. That is, what's that mean? That simply means that drj dt is equal to what? It's equal to A times rj, right? For j equals to what? From 1 all the way up to n. Right? I'm supposing we have n solutions for the sake of discussion. Then consider, what is it if we take the derivative with respect to time of the sum I equals 1 to n of ci ri. Now I'm going to have to use a property of derivatives that I haven't proved, but I hope you guys can forgive me. I'm not going to prove. You don't want me to prove everything in here, right? You'd rather I just tell you how it works. So if we have the derivative of a sum of vectors, and these are constants, the way the derivative works is just the way it did in Calculus 1. We can pull constants out, and we can break over sums. So this is equal to the sum I equals 1 to n of ci dri dt. All right? That's just by calculus. Now what are we assuming? We're assuming that we've got solutions, right? When we plug them in, we differentiate them, they solve this equation right here, right? So I can take this dr di dt and replace it with the sum I equals 1 to n of ci a ri. Did you guys see that? I'm using, by star. Okay? Now I can use properties of matrix multiplication, right? Properties of matrix multiplication allow me to pull the A out front and bring the sum inside, as well as the constants. So this is just basically using distributivity of scalar multiplication and matrix vector addition as well, I think. I have that. And at this point, it's just a problem of pattern recognition. All right? What is this? What have we just shown? Can you see it? If I call this right here R, this is R as well, right? So what have I just demonstrated? I've demonstrated that dr dt is equal to AR. And that proves that a linear combination of solutions is a solution. So the reason for this is what we're dealing with is a linear differential equation. A linear differential equation can be defined by multiplication by a particular matrix, right? That's our definition for the problem, right? Our goal is to solve this. This is the linear homogeneous system of n first-order differential equations. Let me write that out. Let me give you the words. Linear homogeneous first-order system of n ODEs. And I'll write it out. That's ordinary differential equations. The reason it's called an ordinary system, ordinary differential equation, is because there is just one independent variable, time. A partial differential equation would have more than one independent variable. Anybody in here electrical engineering? No? Mechanical? So you guys, at some point or another, will care about partial differential equations, right? Like fluid mechanics is full of partial differential equations, Navier-Stokes and all that. Heat transfer, yeah, also that. So those kinds of, if there's more than one independent variable, you're up against a partial differential equation. Those are trickier, but this is an ordinary differential equation. And for ordinary differential equations, I can present to you a complete and total solution to the homogeneous problem. We can literally solve dr dt equals to AR for any matrix. We have all of the technology we need in here to do that. All right? I mean, I have to develop some results, but first order of business is just understanding the theory, which is simply, one of the bedrock theorems is that a linear combination of solutions is a solution. So we have that. Notice I use that in example 1. my general solution was a linear combination of the eigensolutions, right? C1 times the first one. So this one I will not prove in here, but this is the theorem. The general solution to dr dt equals to AR is given by a linear combination of n linearly independent solutions. Let me say that in a different terminology. If we have an n by n problem and we have n linearly independent solutions, that's said to be a fundamental solution set. Probably should define that. Definition: if you have R1, R2, Rn linearly independent solutions, this is a fundamental solution set for excuse me, dr dt equals to AR, where A is n by n. Now, you might wonder, you might say, hold on a second there. What do you mean linear independent? We have not defined linear independence of functions. You caught me. It's true. I have not defined that yet. But it means what you think it means. It means that they're independent. Like over here, e to the minus 2t times 1 minus 1, and e to the 2t times 3, 1, that would be a fundamental solution set for that problem. Those are linearly independent functions. Without, getting too far afield into the differential equations theory, let me just give you a quick theorem on testing linear independence. Well, there's more, I suppose I should say. All right. So here's, I probably should just tell you the definition. Given R1, R2, Rn, mappings from R to Rn. All right, so these are vector valued functions of time. We say, the set containing these functions, R1, R2, Rn, is linearly independent if C1, R1 of t plus C2, R2 of t plus plus Cn, Rn of t equals to 0 implies what? A little bit more truth in advertising here. For all t in the reals implies what? What was our definition of linear independence for vectors? Remember? Linear combination equals to 0 implies all the constants have to be 0, right. So we just need that this has only the 0 solution. But here's the thing. You can rewrite this as a big old matrix right? You rewrite this as a big old matrix times a single constant vector, C1, C2, Cn, equal to 0, the n0, right? So what condition do we need on this matrix here for the set of n solutions to be linearly independent? So basically, if there even exists, if there exists a time, right? If there exists some time such that that is an invertible matrix, then we can, plug in that time and solve for the constants. The constants can't depend on time. So if one particular time in that matrix I wrote down is invertible, then that's enough, right? So in other words, you can just look at the determinant of, and I'll just write down R1, R2, Rn. This is called the Wronskian. The Wronskian. If the Wronskian is non-zero, that implies linear independence of the solution set. All right. So you could, going back to my example 1, right? Like what would be, I would be looking at the determinant of what would be like my first solution was what? Ignore the constants, right? We had e to the minus 2t, yeah? And minus e to the minus 2t for my first eigensolution. My second eigensolution had what? Was it 3 e to the 2t and e to the 2t, is that right? So ignore the C1 and C2. Those are just part of the solution. The C1 and C2 have to be there to allow for different possible initial conditions, right? Think about it. But what's this equal to? Well, 1 plus 3, so it's 4. So indeed, the solution set there is in fact a fundamental solution set. It's linearly independent. And the theory of differential equations assures me that if I take a linear combination of fundamental solutions, I have captured all possible solutions to that differential equation. That's how the theory works out, all right? Any questions? So what is the task in front of us? The task in front of us is to try to find a fundamental solution set for dr dt equals to AR. All right? That's what we need to do. And I've already showed you that if we have eigenvectors, that gives us solutions, right? Now, why does that work in general? Let's look at that for a second here. Let's talk about how to derive the eigensolution. So before I do that, let me take you back to calculus like 2, right? Do you guys remember being asked how to solve dy dt equals to like, I don't know, I'll say at, just dy dt equals to a times y. Can you solve that differential equation while I'm erasing stuff here? So you separated variables, right? You know, like dy over y is a dt. Integrate both sides. Natural log absolute value of y is equal to a times t plus a constant, right? Then that gives you absolute value of y is like e to the c1, e to the at, and then absorb the absolute value into the constant, like k e to the at, right? That basically was, that's the solution, right? This is exponential growth. Okay, so now we're trying to solve, let's think about it. We're trying to solve dr dt equals to ar. This is kind of like that problem, right? So a reasonable guess, right? Differential equation is always based on a reasonable guess. Would be maybe r of t should be equal to, how about e to the lambda t times a constant vector? Guess that that's the solution. What do you have to do with a solution in differential equations? Well, if you make a guess, you got to plug it back in and see where it takes you, right? And so where it takes me to is that ddt of e to the lambda t times u vector has to be equal to a times lambda, my bad, no lambda yet, a times e to the lambda t times the u vector. Now, u is a constant vector, right? So what does that mean in terms of the differentiation? Can we pull the constant outside the wonder when I move this. Oh well. Sorry, people not here. I think most of you are here today, though. So if you use a constant vector, we can pull it outside the derivative. You guys tell me, what's the derivative of e to the lambda t? It gives me what? Lambda e to the lambda t, right? By the chain rule. And the u just rides along. A e to the lambda t u. Guess what? E to the lambda t is never 0. So we can divide by it. And what do we get? We get lambda u is equal to au. Oh, hey! We've seen this before. This is a what? This makes u a eigenvector with eigenvalue lambda. So we've derived a theorem, which is that if, you know, we have a minus lambda I times u is equal to 0, then we obtain the eigensolution r of t equals to e to the lambda t times u vector, right? That's what this calculation shows, is that anytime you have an eigenvector, you get an eigensolution. All right, well that's comforting because we found lots of eigenvectors, right? But that's not all that there is there? Because there's also those pesky complex eigenvectors, right? What happens there? What about complex? Well, everything we just did here still makes sense if lambda is complex. You may not be familiar with it, but if lambda is equal to alpha plus I beta, where beta is non-zero, then e to the lambda t actually is equal to e to the alpha t cosine beta t plus I e to the alpha t sine beta t. This is, for all intents and purposes, a definition for us. In the case that lambda is complex, we get a complex combination of sines and cosines and exponentials. And so if we have, you know, u is equal to a plus ib, so this is a complex eigenvector, then let me use a z vector equals to e to the lambda t times u. Well, that actually would be like e to the alpha t cos beta t plus I e to the alpha t sine beta t times a plus ib. This would be a complex solution, a complex eigensolution to the differential equation. We multiply this out. What we've got is we've got e to the alpha t. I'll hold that out. Cosine beta t times a minus sine beta t times b plus I times e to the alpha t sine beta t times the a plus cosine beta t times the b. All right, so all I'm doing, guys, is I'm writing out explicit formulas for our reference. This right here is the real part of the complex eigensolution, and not including the I. This is the imaginary part of the complex eigensolution. So let's think about this. We have a differential equation, and we have a complex solution. How does that work? You're like, well, you never really quite defined what you mean by differentiation of a complex valued object, so I have no earthly idea. Why don't you tell me? Fair response. But the answer is that we differentiate complex valued stuff in the most natural possible way. And so let me show you. Here's the definition. So suppose that we have z is equal to x plus iy. Here, x and y are themselves mappings from reals to Rn. So the x and the y are like the kind of, they're just vector valued functions of time. So the way we differentiate a complex valued thing like this is just this. We do dx dt plus I times dy dt. That's how the calculus works here. So let's parse this. We have a complex solution means what? That means that we have dz dt is equal to a times z. That's what we mean when I say I have a complex solution. All right? I have an explicit example to follow this, so hang with me here. But look, so that means that we have d dt of x plus iy is equal to a times x plus iy. But the way we differentiate this is the real part and the imaginary part separate, like that. And how does it work when we multiply a real matrix times a complex vector? I mean, we haven't talked about this a lot in here, but it works the same way as usual. We just have distributive property, and we've got ax plus I times ay. So this, what we're looking at right now, is a complex vector equation. In order for this to work out, notice A is a real matrix, right? A is a real matrix. So let me circle the things that are real. Real, 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 all real. And the only way you can have equality of a complex vector equation like this is if separately the real part matches the real part and the imaginary part matches the imaginary part, which is to say that dx dt has to be equal to ax and dy dt has to be equal to ay. What's that mean? Aha! So the real part of z, which is equal to x, by the way, and the imaginary part of z, which, by the way, is y, are real solutions to dr dt equals to ar. That's the theorem that this proves. Every time we get a complex solution, we get a twofer. We get two real solutions for the price of one complex solution. That's very cool, I think. So, like, do you guys happen to remember a complex 2x2 matrix problem we worked before? I forgot to remember my notes with me today, but I'd like to just write down an example without working out all the details. Maybe I can. Example 4? I don't know where I am. I'm going to say it's 4. So suppose you got a is equal to like 2 minus 3, well, minus 3 down here, 3 up there, 2. So this one, you can work it out, has lambda equal to 2 plus or minus 3i. And I believe the complex, so we can check this. If we look at lambda equals 2 plus 3i, then I believe u equals to 1i is an eigenvector. How can we check? Let's try it. A minus lambda I times u. I have minus 3i, 3, minus 3, minus 3i times 1i. What happens there? I get minus 3i plus 3i minus 3 minus plus 3, right? Hey, look, it worked, yay. Okay, so I remembered something. That's the solution. That's a complex eigenvector solution here, right? So what I'm telling you guys, if you believe me, is that we can write down the solution e to the 2 plus 3i times t times this complex eigenvector. But that is e to the 2t times cosine 3t plus I times the sine of 3t. All right, and then what are a and b here? One, 0, right? Do you see that? A and the b, the real part and the imaginary part of the complex eigenvector, for my example right now, they're simply the standard basis. They're simply the standard basis. So let us finish constructing the solution here. We're trying to find real solutions to differential equations. So we can't leave an I in the answer. And we just have to use the theorem, basically. So this is, 1, 0 plus I times 0, 1. And all we got to do is just basically multiply this out and collect stuff. So I've got like cosine 3t times my 1, 0 minus, can you guys tell me why there's a minus here? I times I is negative 1. We have a winner. Very good. Sine 3t times 1, 0. Cosine 3t times 0, 1. All right, so solution. The general solution then is r of t is c1 e to the 2t times, let's see here, I can put this all together. I've got a cosine 3t there, and I've got a minus sine 3t here, plus c2 e to the 2t And this time I've got a sine 3t upstairs and a cosine 3t downstairs. So that's how we solve a system of differential equations using the complex eigenvector. It's a little bit less direct, but the story is very similar. What we do is we take the complex eigensolution and we calculate its real part and its imaginary part. Those separately have to be real solutions. And they also, because of the details of the mathematics here, they have to be linearly independent. That actually is an automatic consequence of the eigenvalue being complex with a non-zero beta that forces linear independence of the vector A and the vector B in comprising the complex eigenvector. I think I proved that for you guys. And so that's the solution. So let's stop. Take stock of what we know. If we have a matrix and we've got n real eigenvectors for the problem and they're linearly independent, we can just write down all the eigensolutions, a linear combination of those, that's the solution to the differential equation. Now anytime you got a complex eigenvalue, you have to do this thing. And with respect to the complex eigenvector, you get two solutions for each complex eigenvector, right? We don't even need to use the conjugate eigenvalue, right? The 2 minus 3i is irrelevant, doesn't matter. But what else have we talked about the last week? The Jordan form, right? So we know that there's matrices out there which we can't diagonalize, either in the real or the complex sense. And so the question that remains that I'm not going to answer today is how do we solve differential equations where you don't have enough eigenvectors or enough complex eigenvectors? How do you solve those? All right. Turns out the answer is something called the matrix exponential. And we'll see like next class that with the chains that we talked about before, you can just straight solve everything with the matrix exponential. Ultimately, the matrix exponential has in it all of the solutions that you ever need. All right. So with that, let us turn to working on your, remaining problem here in Surprise Attack Mission 9. I was going to take a stab at problem 2 with you guys, so let's do it. Now, did you guys already work out part A like I asked you? Did that at least work? Yes, no, maybe so? All right, well, let me erase myself a little bit of space here so we can, I think that's the healthy thing to do to start with. Now, you're checking something's an eigenvector. There are two paths to go down, right? Think about this. You could either check that AU is equal to lambda U, right? Or you could check that A minus lambda I times U is equal to 0, right? AU is lambda U is the same as A minus lambda I times U is equal to 0. Which one of those do you think is easier to parse, to actually sort through in the context of the problem on your surprise attack mission, or just generally?
The right side.
Definitely the right side, right? Seeing something is 0, that's clear cut. Seeing something's a complex multiple of another complex vector, that's a headache, right? So let's try this on for size. So this horrible, why have I done this to us? So A is, so I'm supposed to look at 6, minus 3, 2, minus 4, 2, 0, 8, 7, minus 4, 4, 1, 0, minus 1, minus 2. All right, it's supposed to take that, allegedly minus the eigenvalue, which was minus 1 plus I,